Here we're going to solve trigonometric equations, but using skills that we learned with quadratic functions. So one of these we already looked at, but that was using the square root method. We'll look at a case using factoring. And then, so square root method's kind of nice when you just have a single, like something squared to solve for. Factoring is usually when you have a trinomial or binomial to work with. Another method will be, if we can't use those, we'll have the quadratic formula to fall back on. So we're going to look at some examples with those different methods. It comes down to the same process. It's just mixing how we solved our quadratic equations along with how we're solving these trig equations. All right, so this first case here, what I want to do is isolate my trig function. Now, that's the way we've been solving so far, and that's actually what I want to do in this case. We'll talk about when we have our quadratic, and sometimes we want to have 0 on one side of the equation. However, here, it's just that I just have this one trig function and it's squared. So what I'm going to do is isolate that so I can use the square root method. So I'm going to add 1 to both sides and then divide by 4. So that should get me that cosine squared of x is equal to 1/4. And then the square root method is that I can take the square root of both sides of the equation. So square root and square root. When we do this, we get plus or minus the solution. So we're going to have cosine of x now, because that root and exponent just kind of cancel each other out. And then plus or minus, because we took the square root of both sides. So we have the positive and negative form of the solution. And then the square root of 1/4 is 1/2. So what we get from this is that we're taking inverse cosine of plus or minus 1/2. So that means we're having an x coordinate that's both positive 1/2 and negative 1/2. So let's go to our unit circle to see what angles give us that solution. So here's my circle, here's my axes. Positive 1/2 is about right there. So we get two solutions from the positive 1/2, and that's happening at pi over 3 and negative pi over 3. Then we also have negative 1/2, and we get two solutions out of that at 2 pi over 3 and 4 pi over 3. So let's go ahead and see these angle measurements that are coming through. We have this angle of pi over 3. We have this angle of 2 pi over 3. We have this angle of 4 pi over 3. And our last one here, to run out of space, 5 pi over 3. So all of those are possible solutions, and actually that will take care of all of our possible solutions on 0 to 2 pi. So let's go ahead and make that list. That angle x can be pi over 3, 2 pi over 3, 4 pi over 3, or 5 pi over 3. All right. Now to make a formula. There are a few ways to go about this. Let's use the fact that the period here is 2 pi. So let's keep that going. What I'm going to do is think of pairs. So like I have this positive pi over 3 and negative pi over 3. So let's go ahead and describe that one. That we would be taking x, where x is defined by plus or minus pi over 3, and then using those revolutions of 2 pi, since that's our period for cosine, and then or, which is going to come from these two pieces. That's coming from a positive 2 pi over 3, And then this 4 pi over 3, I could think of that as negative 2 pi over 3. So those match up as well with that reflection over the x-axis. So I'm going to think of that as plus or minus 2 pi over 3. So, or plus or minus 2 pi over 3 plus any full revolution of 2 pi, where k is an integer. All right. So with that, there's just more possible solutions because of how quadratics work, that quadratics can have more solutions come up than, say, linear. So when we take that square root of both sides, make sure you have that plus or minus so you're seeing all possible solutions. All right. With this case here, I can see I have two trig functions in here. I have cosine and sine. So with that, I'm going to need to make a substitution, and with that I start looking for the Pythagorean identity, which I can use with that sine squared there. So I'm going to make a substitution with the Pythagorean identity that 2 cosine A is equal to 1 minus cosine squared A. Now if it helps, you could rewrite this as like 2x equals 1 minus x squared. That's really what we're dealing with here. It just looks more complicated with these trig functions. But this really shows like we have this quadratic equation. We have an x squared piece, we have an x piece. That makes me think I need to have 0 on one side of the equation. So I want to move pieces around so I have 0 on one side. And typically we move things so that the squared piece is positive. So I'm going to do is add cosine squared to both sides of the equation. So I'll give me cosine squared plus 2 cosine A. And then to really get 0 on this side of the equation, I'm going to subtract 1 from both sides. So then minus 1, and that would just leave me with a big 0 over there. So the equivalent that I have is that I have x squared plus 2x minus 1 equals 0. Now I have a trinomial. So what I would do is try to factor this. So if I wanted to look at this version that we're more used to and start factoring, so I'd have x and x. I have two numbers that multiply to -1, so it'd have to be a -1 and +1. However, that wouldn't give me the 2x in the middle there. And I don't have any other combinations that I could come up with. So I tried factoring, it didn't work. So that tells me that I need the quadratic formula. So, good old quadratic formula. I need to know the numbers that are multiplying with the values here. So I have 1 cosine squared. So that means my value for A is 1, B is 2, and C is -1. So when I go to plug into the quadratic formula, which usually solved for our variable, we always said like x equals, that was what's underneath the square, that's the number there. Here, it's that we're solving for cosine. So instead of writing x equals, I actually write cosine equals, and then I'm going to have -b plus or minus square root of b squared minus 4ac all over 2a. So plug in my a's, plug in the b's, plug in the c. So simplifying this down, cosine is equal to -2 plus or minus square root of 4 plus 4 all over 2 times 1. And then I'm just going to simplify this down. So -2 plus or minus 8 is made up of a 4 times 2. So square root of 4 is 2, and then we still have a 2 trapped underneath. I can divide out a 2 from each piece. So that'll leave me with -1 plus or minus root 2. All right, so this gives me two possibilities. We could have cosine is equal to the addition of those two values, or cosine is equal to the subtraction of those two values. So -1 minus root 2. So, same routine of quadratic formula as we're used to. It's just cosine of A is what we're working with instead of X. We could grab decimal forms of these numbers, or we could just go ahead and look at the inverse cosine of these. That -1 plus root 2 is about equal to 0.4. This one, if you grab the decimal for this one, the -1 minus root 2, you're going to get a number, what was it? Let me write these here. This is a -2.4142, and this is just 0.4142. Now these are giving us the x coordinates. So this second one is saying, what angle measurement do we have that gives us an x coordinate on the unit circle of -2? That's not possible. And if you plug this into a calculator, it's going to be undefined. So we actually aren't going to get anything from that second value. However, this first one, we could visualize. This is telling me we have an x coordinate of 0.4142, a positive x coordinate. So with that, I could visualize, let's see, 0.4142 is maybe about there-ish. So we get these two angle measurements out. I don't know what they are, but if I use inverse cosine in the calculator, that's going to give me a value up here, and I just have a positive and negative version of that. So I'm going to go to the calculator and grab an inverse cosine of a -1 plus square root of 2. And that's a 1.1437. So this angle measurement right here is a 1.1437. And then our second angle measurement's just the negative. So our solutions. On 0 to 2 pi, we're going to have that, let's see, our variable is a. Our angle measurements could be the positive 1.1437. Then I just need the coterminal with that one, so I'm taking 2 pi minus that 1 point, so it's like go 2 pi, which is all the way around, but then we're going back 1.1437. So 2 pi minus 1.1437 should be a 5.1395. And then for making a formula, I'm just going to use the plus or minus of those angle measurements, and then we're working with a period of 2 pi. So with that, A is defined by plus or minus 1.1437 plus 2 pi k, where k is an integer. All right, one more example here with a little bit of factoring. So I can see I have a squared value. I also have a value that's not squared. So that tells me I want to get 0 on one side of the equation. And I want to keep my squared value positive. So I'm going to subtract this root 3 sine of t from both sides. So I'll have 2 sine squared of t, and then minus that root 3 sine of t equals 0. Now with this one, I have a common factor. I have this common factor of sine of t, so I'm going to factor out a sine of t, which leaves me with 2 sine t minus root 3 equals 0. So I just divided out a sine of t from each of those terms, so I have it out front. Then I have my 2 sine t minus root 3 as the leftovers. All right. So now I have this product of 0 rule. I have two things multiplying with each other that give 0. So that means one or both of those pieces need to equal 0. So either just sine of t equals 0, or 2 sine t minus root 3 has to equal 0. So sine t equals 0. We still have a little solving to do. I need to look at this inverse sine of 0. Over on this right-hand side, I need to move things around a little bit. So I'm going to add the root 3 to both sides and then divide by 2. So that should give me sine t equals a positive root 3 divided by 2. And then I just need to look at the inverse of that. So inverse sine of root 3 over 2. All right, so this one branched into two separate equations. So with that, I'm going to make two separate unit circles to look at. So let's just look at the case of 0 first. So this inverse sine of 0 is saying what are the locations where y is equal to 0? And that's happening in two locations. Y equals 0 is happening here at 1, 0 and negative 1, 0. So we get two angle measurements there. We have an angle measurement of 0 and an angle measurement of pi. I'm just going to list those there, 0 and pi. Then our other case is taking that inverse trig function with y equals a positive root 3 over 2. So with that, my unit circle or oval that I'm drawing there. Let's see, y is the long side of the triangle, so that should be happening up here at pi over 3 and 2 pi over 3. So we have a pi over 3 and 2 pi over 3. All right, so t equals pi over 3 or 2 pi over 3. So on 0 to 2 pi, you can just list those out. We have a 0, we have pi over 3, and we have 2 pi over 3. In terms of a formula, I'm going to think of these separately. In fact, I'm going to come up with a few equations here. So using this first circle, I can relate these pretty nicely to each other because like the angle measurements will be 0, pi, 2 pi, 3 pi, 4 pi, 5 pi. It's just moving intervals of pi around there. So one of my equations for t is defined by, is just going to be pi times k. We're going to have any increment of pi coming up because of that first circle there. So that takes care of that one. For the second circle, when we had those reflections across the x-axis, it's fairly easy to make up with that kind of plus or minus. With this one, and there is a way to relate them, but it just gets kind of, ends up being more work than it's worth. I need to think of these just separately. So I want this pi over 3 and any interval of 2 pi around that value. And I want 2 pi over 3 and any interval of 2 pi around that. So I'm going to have two separate equations for those. So, or t can equal pi over 3 and any increment of 2 pi, or 2 pi over 3 plus any increment of 2 pi, where k is an integer. All right, so that's how quadratics will come in. If it helps, you can replace those trig functions with x or just a variable and kind of work through how you would solve that usually. But then you'll get to this inverse trig part where you'll need to go to the unit circle and then think about those values 0 to 2 pi and then make the formula.